Start up again in just a minute.
Yeah, just one thing I wanted to mention before we start. I have forgotten a very important fact in my talk. Everything that I was describing about CO2 condensation, it's available in Planet 2 release, but it's not actually available in Planet 1.0. So you have to either wait for Planet 2 if you want to use it, or just download basically a beta version from our website for Planet 2 if you want to experiment with CO2 condensation.
Great, thanks, Igor. Okay, Kostas, why don't you take it away and discuss equilibrium, and then we'll move on to Eric.
Okay, so that will be quick. The point is that when you start the model from any initial conditions, it is virtually impossible to have a planet that is already in a proper equilibrium to do studies. Chances are that the planet will be in some other state, and then it needs to go to equilibrate itself dynamically until it reaches some steady state, and then you will be using that for your analysis. We call this time period that passes from the cold start of some initial conditions to the equilibrated state as the spin-up time. And this spin-up time depends on several factors, and they depends also on model configuration. So if you're using, for example, a planet that does not have an ocean, this spin-up can be very, very quick because radiation will equilibrate pretty quickly. If you are using a planet with a very deep ocean and you are having dynamic ocean calculations, then the ocean will take a lot of time to equilibrate, and then your equilibration time might be thousands of years. So it really depends on the case. It also depends on whether you care about certain diagnostics. So there are things that matter for climate a lot, and there are things that are just, you know, the cherry on top, and they don't really matter too much about climate. And if for certain variables you are off equilibrium, it might not really matter for what you're asking. So the single most important parameter that you need to care about is this that you see on the plot on the top here, which is called net rad planet. You can find it in the AIJ file that Igor is one of the files you get from Scale ACC that Igor was describing yesterday. And so this shows whether the planet it gains or loses energy. So if it is positive, then it gains energy and it heats up. And then if it is negative, it loses energy and cools down. And at equilibrium conditions, this value should be fluctuating around zero. It will not be exactly zero. It will not be even near zero for any individual time. The annual mean of this, actually the orbital mean, is going to be going up and down, as you can see in those lines here. And but the overall decadal or 50-year mean or X number of orbits mean needs to be near zero. And we have a soft choice to make that it needs to be at least 0.2 watts per meter square from zero, but that is not always possible to achieve. So you see here, for example, these are different runs. It doesn't matter which one is which. You see that the dark blue line is equilibrating very fast, and it is fluctuating quite a bit by about a watt per meter square. But the overall decadal mean that you see with the thick blue line right in the middle is fluctuating around plus 0.2, which is pretty good. So this simulation equilibrated quickly. And then you have the other two simulations that you can see with this gray-green thing and the cyan, that you can see that they, over the course of 500 years, which is this plot showing, the value is pretty high. And it does go down to zero. Eventually, it looks like it will go down to zero, but it's not there yet. And what happens is that this planet is having a positive radiative balance, which means it warms up, as you can see at the bottom plot with the surface temperature plot, that it goes up and up and up until at some point it will reach some equilibrium. So other than the net rad planet, which is the important one, another important thing to keep in mind is that eventually a planet with a dynamic ocean will reach equilibrium. But there are some other cases that your planet might not. And the most typical one is that if you are simulating a planet with prescribed sea surface temperatures, and those prescribed sea surface temperatures are not near the one that are at equilibrium conditions. So what happens then there is that you are throwing energy on the planet. This energy needs to be uptaken eventually by the ocean, but the prescribed SSTs do not allow that. So this energy is getting lost and you are not warming up the ocean. So you're not warming up the surface air over the ocean properly enough. And then the only warming that you will be seeing is over land. Plus, this will not be enough of a warming from what the planet is expecting to do with the radiation it's receiving. So it will keep warming itself as much as it can based on given the prescribed SSTs, but you will never be able to reach equilibrium. So there are two ways to do that. One way is that you fix your SSTs to something more realistic for that planetary configuration, or the more typical thing that we do is that we change the planetary albedo by altering the balancing parameters for the clouds we have for the high clouds and low clouds. So for Earth, for example, we know what the planetary albedo is from measurements, and we're trying to match that number with changing the cloud distribution balancing parameters that we have to create a proper planet that has the prescribed SSTs that we know are correct because we measure them, and then the albedo of the planet that we know is correct because we measure it, and then have a net radiation balance of 0 for pre-industrial conditions, because we know the planet is warming up right now, today. But back then, when the human impact was very small, it was 0. So there are ways to go through that, but on a new imaginary planet or a real planet that has been detected and you don't have any of those information, then the best thing you can do is that you either assume that this planet is a land planet and then it will reach equilibrium very quickly. Or if you are assuming that this planet has an ocean, either a water world or not, or just partial water cover, you need to have a dynamic ocean enabled in your simulation so that the planet will eventually reach equilibrium. And again, it might not happen immediately. It might not even happen. We have a few cases that we were never able to reach the 0.2 criterion, but most of the time you can make it. So other than this key parameter, there are other things that one might look at. So this is a simulation for 1500 years this time. And you can see with a green shade how the different variables on the left fluctuate with time. And you can see the 0 is the red, the equilibrated conditions are the dashed lines based on the last maybe 100 years. Mike, I think it's 100 years that you're using, right? Or 200 years?
Last 10 years in this run.
Just 10 years, okay. So last 10 years in this run, you see the dashed one. And so you see the variability, you see how the long-term mean with the black line goes, and then certain things equilibrate, like the ocean ice fraction at the top or the ground ice in the middle. The sea ice thickness has not equilibrated yet because it keeps drifting upward. The snow depth is, I don't see a black line here, but it looks good. And then the last one is interesting, which is the mass of water in lakes, that you see that it keeps increasing. And this is an excellent example of something that is in the hydrological cycle that has a very long memory, and it needs thousands of years to reach equilibrium. And this is because we are having variable lakes. So what happens is that there is lakes in this configuration we want to keep increasing, and they grow and they keep growing, and water is being dumped there until the lakes reach the equilibrium condition. However, this change is not very big in general for the climate, because you see that most of the other climate parameters are not being affected much. So it's a good example that you might say, you know what, my planet equilibrated in almost everything I care about in 1,000 years. I don't have to wait 5,000 years only for this one variable to equilibrate itself. So this is how it goes most of the time. So the key things that you care about we have equilibrated are net rad planet, which is the net radiation of the planet, the surface air temperature, the sea ice fraction, probably even thickness. So maybe this run is not equilibrated properly yet. And in general, things that matter to your own questions. Any questions? I see the chat window blinking, but I have not been paying attention to it.
That's just me describing the variable names.
Okay, perfect. So any questions for that, or we move to Eric?
I think we better move to Eric because we're running a bit late.
Okay, so
save your questions for the Q&A.
Okay, perfect. So Eric, you want to share your screen, or you want me to click on the next one?
You can just click through, and I'll just kind of cue you to click me forward.
Perfect.
Thank you. So hi, everybody.
So quickly, this is Eric Wolf. He's our radiation person. He's going to give us an introduction. Go for it, Eric.
All right, thank you. In ROCKE-3D, it uses a radiative transfer model, which is an amazing backronym called SOCRATES, which is a suite of community radiative transfer codes based on Edwards and Slingo. Next slide, please. So first, for some people, this may be completely obvious. For others, this may be new information, but just what is radiative transfer? So the transfer of electromagnetic energy through a medium, and that medium being the atmosphere. So that is how the sun's energy filters through the atmosphere, whether getting scattered by Rayleigh scattering, scattered away by molecules, reflected by clouds, reflected by the surface, absorbed in the near infrared by water vapor and other species. And then you also have your thermal radiation component, the greenhouse effect. Energy in longer wavelengths is emitted by the surface. It's absorbed by gases in the atmosphere and re-radiated back towards the surface. Greenhouse gases to CO2, water vapor, methane. High clouds also provide a greenhouse effect. So radiative transfer, both in the short wave and the long wave, in large part determines the energy balance of a planet and thus the temperature and climate of a planet. And it is really important to get radiative transfer correct as we move towards exoplanets and other worlds, because it's often very different from that on the Earth. So next slide, please. All right, so in any planetary atmosphere, you'll have scattering and absorption by different gases, and clouds and aerosols, emission or reflection by surfaces, different ice surfaces, land surfaces, ocean surfaces, by the atmosphere itself. On the right, we have just a simple illustration of the primary absorbing gases in the Earth's atmosphere. So in the red, you see the solar energy that's incoming from our sun. And then the blue, the long wave radiation emitted by the planet. And then the middle panel here is the total absorption and scattering as the sum of all these different components: water vapor, carbon dioxide, oxygen, ozone, methane, nitrous oxide, Rayleigh scattering. So all GCMs have a radiative transfer component, which is incredibly important for calculating climate. But what's more challenging is making sure that the radiation is flexible enough so that we can change the stellar spectrum, change the different gas species, etc. in the model and still have it do a good job. So for instance, if you think about this solar spectrum up here in red, we often think about planets around M-dwarf stars are a really hot topic because they're easier for us to see planets around. That stellar spectra is shifted significantly into the infrared compared to this sun spectra shown here, which means as you can extrapolate down to these bottom plots, which show the absorption regions for different gases, that different absorption regions will all of a sudden have a different weight of importance as you start to shift your spectra around. And then obviously when you start to shift your gas amounts, if we're not just talking about doubling CO2 or CO2 inching up over a century, we're often thinking about what if we have a pure CO2, Mars-like, early Mars-like atmospheres? What if you have 2 bars of CO2? So it's really important that we get all these aspects right in the radiative transfer. Next slide, please. So SOCRATES, it's a radiative transfer model designed specifically for use in 3D climate models. So there's 3 requirements. It has to be flexible, it has to be fast, and it has to be accurate. So in GCMs, the radiative transfer calculation is called for each column in the model. So in our nominal 4x5 resolution, that's 3,312 columns over the planet. And oftentimes it's called once per hour. So in the course of a 1,000-year run, you're talking about tens of millions, I think hundreds of millions of actual calls to the radiative transfer over the course of the run. So it's got to be fast. You can't use a line-by-line code, which would be the most accurate, because it's just going to be way too slow. So you must balance these. The fast and accuracy have to be balanced. And then flexibility is something that many radiative transfer models can struggle with, but SOCRATES is a built-in framework from linking a 1D offline version with correlated K production tools that can be piped straight through into the 3D model, into ROCKE-3D quite easily. So SOCRATES really checks off all 3 of these boxes of it's flexible. We can design the absorption coefficient sets to be fast enough and accurate enough in that nice balance. So some key terms to remember when you're using ROCKE-3D. So spectral files. So this is what we refer to. These are the absorption coefficient sets that we use in the model. So they're tailored sets of gas and aerosol absorption coefficients. And in the term aerosol, I'm also lumping in clouds with that. Used in SOCRATES, that we use in ROCKE-3D as well. So both offline SOCRATES and in ROCKE-3D. In the run deck, they are the variables spectral underscore, I'm missing an underscore there, spectral underscore file underscore LW, spectral underscore file underscore SW. So there's a different spectral file for both the long wave and the short wave, which we've at this point constructed myself, and most of the credit has to go to my present predecessor in this role, David Odmundson, who did the first lead linked SOCRATES with ROCKE-3D, and I've picked up in his absence. So we have a number of different spectral files that have already been created for the early Earth, for Mars, for Titan, and then these are all available. And in the next slide, don't switch yet, but in the next slide, I'll show you the web links. The next, of course, key term is the stellar spectra. Sort of obvious. The incident stellar, one novel thing in ROCKE-3D is that the incident stellar spectra is convolved with the shortwave spectral files. So in some other GCMs, you have a fixed set of absorption coefficients, and then you just swap out the stellar spectra at your leisure. With ROCKE-3D, that's one thing that's a little bit more complicated. I mean, it's not complicated at all. That's the wrong word. One extra thing to keep in mind when you change your solar spec in the run deck, you also need to make sure you have the matching shortwave spectral file Now, convolving the two together, the stellar spectrum and the shortwave spectral file, gives us a little bit more accuracy for our shortwave radiative transfer. And then finally, this isn't, I guess, native to SOCRATES in particular, but when you're thinking about radiative transfer in planetary atmospheres, you're also thinking about the incident stellar flux setting at planet S0. So, and in addition, as was I believe talked about earlier, changing gas composition of the atmosphere, which I didn't list down here as well. So those are when you're thinking about radiative transfer in a planetary atmosphere, you're going to be thinking about a different stellar spectra than the sun, a different incident stellar flux than the sun, and most likely a different composition of gases, which is set elsewhere in the run deck, but fed into SOCRATES. And then you'll have to choose your spectral files, which are most closely aligned to what your planet is, the atmospheric composition of your planet, rather, and then make sure that your shortwave spectral file has the same stellar spectra that you're using. And all these spectral files in the shortwave are tagged by their stellar spectra in the directory, so you can't, you can't confuse it. So next slide, please. Oh, next slide, please. Thank you very much. All right, so this is a list of resources. So what's not on this list is you can email me, and I didn't put my email address up there. I think it's elsewhere in the presentation though. And then these are our resources for everybody to use. So the first one up here is the ROCKE-3D SOCRATES user guide. So how SOCRATES is implemented into ROCKE-3D and how a ROCKE-3D user interfaces with that. The next document there is a list and description of spectral files that I had just talked about, and also has a list of the stellar spectra available. And at this point, we have a wide variety of terrestrial planet atmosphere spectral files completed, and we have a wide variety of stars ranging from TRAPPIST-like stars at 2600 K all the way up to the sun. I don't think we have a lot of stars veering into hotter stars like F stars, for instance, but we have a tremendous amount from G, K, and M stars at the moment. But it's not too hard to make new spectral files and make new stellar spectra, and you can contact me. That's one of my roles here, is to do things like that. So if there's something you need or you're interested in, please contact me. And then the final two here are, I should have mentioned before, so SOCRATES is a UK Met Office model that's also linked with their GCM as well. So they maintain the master source code for SOCRATES, and they also provide excellent documentation that if you're interested in getting into more of the gory detail, you can look at their technical description of the inner workings of SOCRATES, the radiative transfer equations used, and things like that. And then also the SOCRATES user guide provided by the UK Met Office, which gets into all the many different options offered in SOCRATES for two-stream approximations, or how you do some of the back-end stuff, how you make the correlated K absorption coefficients, etc. So this is my final slide on SOCRATES. I didn't want to belabor it too much, but I hope to stress that getting the radiative transfer right is an important part of any planetary GCM. And SOCRATES is a great tool that provides us with a nice balance of flexibility, speed, and accuracy. The one drawback, I might say, with SOCRATES is that the user, there's a little bit of a if you get in depth into making your own spectral files, there's a little bit of a learning curve, but that's true with anything. So if there's any questions about SOCRATES, I'd be happy to answer them now, or feel free to contact me with your own questions offline as well.
Great, thanks, Eric. If there's a quick question, we could try to answer it now. Otherwise, I think we should try to move on. Okay, I don't see anything. Okay. All right, so I think we should move on to Geronimo, and I think he's already got control of the screen.
We do have one question. We do have one question on the chat window. Eric, can you see it?
Yes. Is this from Igor? On non-eccentric orbits, do the mean distance and the solar constant parameters essentially do the same thing? And then Chris Kolos has answered, the flux will be planet zero divided by the mean distance squared. So yeah, the on that ties in with the orbital computer. When you set planet S0, it's a mean flux, and then that flux received by the planet will change in time as the distance between the planet and the sun changes based on the orbital computer calculations.
Exactly. Great. Okay. Thanks, Igor. Thanks, Eric. All right. Why don't you take it away, Geronimo, and it's going to show us some exciting stuff.
Perfect. So can everybody hear me?
Yes.
Okay, great. So, well, thank you, Eric, for talking about radiative transfer. So yes, as you heard from Eric, so the radiative transfer plays a massive role in computing the properties of the atmosphere, the temperatures, and the equilibrium state of the atmosphere. And for that, you need a fast and accurate and a lot of calculations because it has to be done, pixel point by point across the whole column. So I'm going to be talking to you about something called the planetary spectrum generator, which is also a radiative transfer tool. But the main purpose of the tool is to synthesize spectra of how the planet will look like if you be using an observatory. So the idea is the tool allows you to compute the spectrum of a planet, the whole disk and parts of the disk, and also to do transit spectroscopy and also to compute noise. For example, you can say, I want to see how my planet looks like with KEK, and it will allow you to see that. So, so what is this planetary spectrum generator? So effectively is a tool which is online. So there's a website, and the website can be found up here, which is psg.gsfc.nasa.gov, and that is what we call the web interface, the GUI, the graphical interface for it. So you can go to that web interface. You can pretty much run everything with the GUI. At the same time, we are all programmers, so at the end of the day, we want to script things. So there is also a capability to run all these processes via a scripting language. We call it the API, Application Program Interface. So effectively, when you want to synthesize the spectrum of a planet, you need to define three main things. The main thing is, of course, the geometry. You're going to be saying, okay, I want to do a transit. So you're going to put the planet in front of the star. You want to do a secondary eclipse, you're going to put the planet behind the star. You want to do coronagraphy, you want to put the planet to the side, things like that, no? The other important thing is the atmosphere, and this is what ROCKE-3D is so important for the complementarity between PSG and ROCKE-3D. So then you have to define what the atmosphere is made of. So once you have reached your equilibrium, so once you reach your atmosphere, you know where the planet is, the equilibrium state of the planet. Then you put the planet in this orbit relative to the star, and then you can provide three-dimensional atmosphere abundances and PT profiles for every location on the disk, and then you can compute spectra for that particular state. And the third parameter is what the telescope you're using. For example, say I'm going to be using LUVOIR, I'm going to be using James Webb, I'm going to be using KEK, and this is where you define the wavelength range, the resolution you want to do, the noise performance, and all those things are being in that thing. So effectively, when you run the tool, you need to define three things: geometry, atmosphere composition, which is going to be the link to ROCKE-3D, and the third thing, which is the instrument you're going to be using for that. So in summary, the tool is a combination of all these blocks here. So first of all, as Eric was talking about, a big element of any radiative transfer core is what we call the line list, or where every molecule absorbs and radiates light. And those come in different forms. There are multiple databases. The more complete your radiative transfer, the more access to more databases it has. So with PSG, we have access to a lot of databases that allows to be much more, very You can pretty much synthesize any atmosphere, any compound. You can also synthesize things for the surface. So as you know very well, you can have a flat albedo or a common albedo, but you can also put, like, you put some ices on the surface and stuff like that. So you can also define the properties of the surface and the solid phase of the planet, but also the atmosphere. And this is where ROCKE-3D comes. Once you have all these databases, then you need to tell where the gases are in an atmosphere. You will tell, okay, my atmosphere has this temperature, this pressure at this location. These are the molecules abundant there, and this is where you provide the linkage with ROCKE-3D. And I will show you how you can take the outputs of ROCKE-3D and the netcdf files and actually convert them directly into inputs for this code. And the last block, you can also define properties of our instruments. We have different models for different observatories. So effectively, you can say, okay, I want to make a simulation with James Webb, and it will pick performance, like size of the mirror of the telescope, things like that, and it will be able to give you noise and performance sensitivity stuff. All of that is combined into the radiative transfer code. This is what's similar what Eric was talking about. Is the way, once you know layer by layer where things are located, then you do the integrals about the opacities and the scattering processes, and then you compute an effective top of the atmosphere fluxes that you see. So effectively what PSG can do, it can synthesize pretty much anything from 10 nanometers to 1 millimeter. So it pretty much synthesize from UV up to the radio, and it can also do it from any observatory. The neat thing about it, it has a 3D calculator, so it tells you where every planet is in the sky right now, and you can tell me where this planet is, and it will tell you the orientation between the stars. So it's very helpful when you might make predictions about the distance between the planet and the star and things like that. And it has you can also do so, because this is a tool you want to compute a spectral once for making how the planet looks like. You can add a lot of sophistication, so it means that you can also do line by line, correlated K, multiple scattering, all these things you can play around. So remember one thing, as Eric was talking about, once the atmosphere is stable and you know where the pressure and the temperatures is at every location, then the atmosphere is already steady state, we can say, it's stable. Then you can do line by line, correlated K, you can follow the photons as they go through the atmosphere with any technique as you want. Because now what you care is more about the spectral signatures coming out of the planet. And also, as we say, in the different observatories. And it's nice that Eric showed this plot about the balance. So in as you go deeper into this thing about radiative transfer course, the main thing about it is that how complete they are in all the processes. As you can see, there are multiple processes: scattering, self-absorption, surface interactions. All those things are a little module, we can say, within any radiative transfer. The more of those blocks are being captured by the model, the more accurate and the more reliable they are. So PSG is a tool, is a planetary spectrum generator tool, and within the tool there are modules that the tool calls to do different things. The one we care more for doing the things for planetary atmospheres is called PUMAS, which is the radiative transfer course, like SOCRATES, as we were talking about for the ROCKE-3D. This is the one that captures the information from the atmosphere and the line lists and put them all together and give you a spectrum out of it. So you're wondering, if you already have something like SOCRATES, why do we want to go to the next stage and put another radiative transfer core? So the thing about PSG is that allows you to follow the photons as seen from the perspective of the observer. In the case when you do energy balances on a planet, you mostly care about what comes in and what comes out. That is the energy balance, is the net flux coming into the planet. So what you care is to see how much heat is going to be delivered into the atmosphere. When you want to measure the planet, what you mostly care is what is actually observable from the planet. So you have a different perspective also, how the planet looks from you and to the star and yourself, the planet, star, and yourself. So directability is important. It's not the same to see the planet from the side, that from the front, and reflectance, and all those things they look different, especially with scattering. So this is a simulation, for example, that I did actually during the weekend, showing how a sunset will look like for different planets. This is actually done with the PSG tool. I just look at a set of colors, which are different wavelengths in the optical mainly, And what I did is I play around and I just see how a sunset will look in different planets. As you see, here's the azimuth. So this is if you look at the planet around your the thing, and the sun is moving across in the horizon. You can see, as of course we have blue skies. As the sun starts to go close to the horizon, we start seeing the typical reddish color. That is called Rayleigh scattering. It produced that, our sunset looking reddish. If you add some clouds, so the thing is about when you add clouds are no longer behaving like a Rayleigh scatter. It's not molecular scattering, but it's now Mie scattering, which is much more directive, and it behaves in a different way. As you can see right now, once the sun starts hitting the horizon, you start seeing this glow there going up around there. It's much more directive, it's much more localized. So now directibility, your orientation of the observer and the sun and everything has to play a massive role in how much flux you actually see. So directibility is important. In the case of Mars, you see these typical bluish sunsets, which are happening on Mars, and then in hazy Titan, we see this reddish color, mainly because of the hazes on organic hazes on the Titan atmosphere. So the main point about trying to talk about this is that the importance of keeping track of photons in a very precise way when you do a full calculation from the whole planet. So right now, one of the good things, what I think is most important for PSG, has access to a lot of databases. So you can actually, once you know the state of the atmosphere with ROCKE-3D, then you can start playing around and say, okay, what happened if I add ethane? How did the ethane signature look on the planet? And has access to more than 1,000 molecular line lists, so you can play with different isotopes. You can, it's a good way to check, once you know the composition of the atmosphere, you can play with isotopic abundances or rare molecules, and you can explore how the signatures will look in a spectrum. And it has pre-computed scattering modes, so you can also play with different aerosols, and like typical dust, water ice, organic hazes, and then you also can put them at different locations on the planet, and then see what the impact on the spectrum will look like. And of course, for surfaces, it has a lot of compounds, mainly from different reservoirs, different databases, also more than 1,000, 2,000 components. So I think the main purpose of what I was talking about is something that we added recently. It's called GLOBS, or Global Exoplanetary Spectra. And this is a way to effectively collect information, three-dimensional information from something like ROCKE-3D and give you one spectrum. Because effectively, let me show you here. When you see a planet, you see fluxes coming from all across the globe. You see flux coming from the center, from here, from there. You're getting all the illuminations coming from everywhere. So what you have to do, you need to collect photons from every location on the planet and then add them all up to give you a spectrum. And something that this is the thing that we wanted to talk about today, about the ROCKE-3D interaction of PSG. And effectively what we do is we take ROCKE-3D numbers for every single grid point, and it computes the spectrum as it comes to you with all the right angles, scattering angles, phase angles, relative to you and the observer, and it will give you a spectrum for every location on the disk. Then what we do, we add them all up based on the area, every beam, the perspective area of every beam, and then it will give you the spectrum, the collected spectrum from the planet, the whole spectrum, as it was seen from the observatory. Of course, there are two possible ways to see a planet. The most common actually is the transit. What effectively what you're looking in transit is you're not looking at the planet itself, you're mainly looking at the absorption at the limb of the planet. So if you put the planet in transit, you don't care much about what's happening here, but you're looking at this thing. And remember, if you're in transit, the star is here, this is the planet, you're looking at the night side of the planet, and you are looking at the terminator limb in some way. If you look at direct imaging, in that case, you're looking at the illuminated side of the planet, typically by coronagraphy or some other technique that allows you to see the disk of the planet by itself. And then what you do, you have to collect fluxes you have to compute fluxes for every single location and aggregate them all together. And this is what this tool called GLOBS will allow you to do. So this is a movie. Let's see if it shows. This is a movie how the interface of GLOBS look like. So effectively has a nice GUI interface to see, first of all, that allow you to visualize the outputs of the GCM. It's a visualizer initially also. So the first thing you will do, and I will show you in a bit, is you upload the ROCKE-3D file into the tool, and it will allow you to see the fields in different ways. You will plot winds and different parameters, so you can see how the planet looks like, just to make sure. It's a good validator also to see that the tool understood your points in the right way. So the first thing to do is to ingest those things into the tool, make sure that the numbers make some sense, they pop up in the right way. Once you're happy about it, then we're gonna synthesize spectra, and I will show you how it's done. So right now, PSG can allows to integrate templates. Allows you to convert things from different GCMs. So effectively, just to give you why we need to, why there's a difference within the different GCMs. Remember, GCM output files are huge. We're talking about gigabytes. Some of them are humongous. We cannot just upload a massive file into a server. It will take too much time. And most of the information is diagnostic inside those netcdf files. So the first thing we need to do is to collect the three main files of ROCKE-3D, and I'll show you in a little bit about it. You take those three files out of the ROCKE-3D code, and then those files will transform into a binary file that is understood by PSG. So that is what we call conversion templates. It converts the netcdf files from outputs of ROCKE-3D into a single file that is understood by PSG. We have created conversion templates for free GCMs, the LMD, ExoCam, and ROCKE-3D. So you can just run the script. It's a Python script or IDL, and you can run that script, and it will convert the netcdf files into a binary file. So the first thing you have to do is you have to do that. You have to run the script and convert first into this PSG type three-dimensional file. So this is the second stage here. Then you go to the glob site, and I will show you in a bit. Then you go and say, click on a fitnesses load GCM data, and then you tell the file name and upload it, and then you should be able to see in the 3D visualization how the netcdf file looks like. Then you select, okay, I want to do transit, I want to direct imaging, and I will show you in a bit how it's done. And then you say generate 3D spectra, and the machine will start computing spectra across the planet, and it will give you one spectrum out of that. Okay, so that's the basic principle. Of course, I just told you a lot of stuff, and you're wondering, well, how do I actually do all this? And I will try to be as detailed as possible. But of course, you can also contact me, and I will tell you more in detail how it's done. But I will try to give you a couple of examples so you familiarize how this actually is happening. So if you have a browser, you can actually go right now and to that website and run it yourself. I'm gonna run it right now. So let me a second. Okay. So if you go to the website, and let me show it again for people. So it's psg.hfcc.nasa.gov, and you will see something that looks like this. And you say, okay, great, but what do I do now? So effectively, just wanted to familiarize with the tool. So as I was telling you, there are these three things that you have to always remember when you're running the tool, that there are these three blocks of information that the machine needs to do every single simulation. And remember, every time you put generate spectra, it's going to give you a single spectrum, which is a collection of a lot of points, or a single spectrum. But remember that for any simulation, it requires three things. So one of them is the location of the observer. So we're going to say, if you come here, so the location of target and geometry, the planet. Then you're going to tell the atmosphere structure, the temperature profile, the molecules in the atmosphere, things like that. And this is what you tell, okay, I'm using this telescope and this wavelength range, and I want to have this resolution for my simulations. So I give you, so if you come here to the website, you see something like this. You can click on these slide things, and we can click a synthesize one. So for example, if you click in this one here, it will give you a transit for something like a giant planet. And you see, so I give you, in this case, give you the spectrum of the planet, give you the error bars, because we assume some sort of James Webb-like sensitivities, and it give you for this particular unit. So it tells you what is the transit for this particular planet. So in this case, this simulation was done for this. It also give you the different molecules where they absorb, and of course you can do zooms here. This is the good thing about Plotly. And if you want to download the spectra, you click here and it will give you the numerical numbers you can plot. You can use your preferred tool to make the plots. So we say, well, great. So how did all this happen? So for this particular simulation, the three elements, the three blocks of information, and I'm going to show you then the ROCKE-3D one, were this. So first of all, this is the planet GJ1214b. So the diameter is like this. This is the density. It knows that it's going to be like a Neptune type planet. We say that it's located at this distance from the star, and then we told that we are 14.65 parsecs from this, and we're using an observatory to look at the planet. And in this case, you see this is the star, and we are in transit mode. So in the tool, you can click here, the different conditions. You can put the date and time, and it will give you right now. For example, if you put now, it will give you the location of the planet right now. And this is where the planet is right now for GJ1214b. And if you put transit, it will tell you when the next transit is, which is going to be at that time UT, and it will be in front of the star now. And if you put S, it will be in secondary mode. You will be now, you are behind the star now, and this is what people normally call the secondary eclipse. And all of this defined by the main important thing when you're looking at the location of the planet is the phase, which sometimes it's confused with season on a planet, but it's not always related. So, and this thing is this number here. So if I put here 90 degrees phase, you see now the planet is to the side of the star, and you can see that this is a good case for coronagraphy. This is the maximum elongation or maximum distance between the planet and the star, the maximum distance you can get from the planet. And you can see we are looking at half nighttime, half daytime. So the simulation for this is, you're seeing a mixture of different weathers on the planet just by looking at this particular orientation. And if you go back to transit, you can see we're pretty much looking at the night side of the planet. And if you are in secondary, we are behind the star, you are pretty much looking at the day side of the planet. So remember those things about the configuration. But I just wanted to show you what goes inside the tool in the case of the geometry. The next thing is that it goes into this is the atmosphere. So this is where ROCKE-3D comes into place. So first of all, you need to know the pressure and temperature profile and the abundances for every location across the planet. For most simulations done with PSG, we assume that the planet is homogeneous. That means that the pressures and temperatures and everything is the same across the whole planet. Of course, it's not right, but that's the typical way that pretty much everybody's been doing things for when they don't have access to ROCKE-3D or a GCM code. So the idea is that you will, instead of giving a single PT profile or single abundance profile, you can actually be able to provide for every single footprint any of them. And this is where I will show you what globes is. What it effectively is doing is it's going to give profiles for every location on the planet. And then you come here and you define the telescope. You here define the frequency range, the wavelength range. You say, okay, I want to do it for this range, the resolution of your things, and what units you want your flux. You can want it in any physical unit you can think of. Normally for exoplanets, people like about contrast things or IRF, things like this. And then you also define things about the size of the telescope, things like that. For example, you can also pick a template, and I will show you, for example, if you say James Webb, NIRSPEC, high resolution mode, and then these are all the numbers for this particular telescope. You can pick LUVAR, Eclipse, and it will give you the chronograph performances. So pretty much every time you load a template, it will tell you more or less, you define everything. So you saw how these things are fitting and say, well, okay, show me how we can use all this to actually do a full 3D calculation. And this is where these thin globes come into place. It's kind of a way to parameterize all these things in an automated fashion to give you spectra. So you do like this. You're gonna go up here, it says applications, and it says here, globes planetary mapper, and it's the item here. So if you never run it before, this is the default. It will show you something look like this. This is data from Earth, of course, as you can see. from taken from NOAA, and you can see it's a good way to visualize. You can do zooms, you can play with the planets and stuff like that. So you can pretty much it's a good way to visualize information about the different variables. And now what I want to show you, for example, a quick sample, and these are, so this is, you can pick the variables. In this case, we only have winds and on the surface. So not a lot of information here for this. Is mainly visualization thing. But I'm gonna show you some templates here, which are a good way to start playing around with things. So these are simulations taken from different GCMs. So for some, this is the ROCKE-3D. We can even show this one. This is the file. If you do load template, it shows this is a simulation that I got from ROCKE-3D for Earth simulation. So you can see this is now being shown temperature. You can show nitrogen. Well, these are pretty much the same everywhere. This is the water abundance, and this is for some of the oxygen. And you can also define where and the altitude. These are the different layers, so you can pick the location and the altitude. If you move on the zoom, it will allow you to see the locations. You can also play with the thing. You can remove interpolation, things like that. So again, this is all visualization. Importantly, the first time you run this thing, it's good to do this check. So the main thing is that I'm going to run one simulation with these templates, and then we're going to go ahead and do it with an actual NetCDF file from ROCKE-3D. So let's imagine the case that we pick this exocount, or can pick this one, but it's the same. We pick the planet. So this is an aqua planet, and what we've shown here is, okay, these are the winds on the planet. It has a very peculiar fashion because it's the classical thing from this synchronous planet producing this hot side on the planet. This is the day side. As you go to the night side, you see that the winds are different. And if you put the temperature, the surface temperature, you see it's pretty warm at the subsolar point, and then it gets pretty cold. So once you have the planet, this is just to visualize the planet. Say, okay, I want to get a spectrum for this planet in different conditions. So how do you do that? So this is where you start setting the setup of your scheme. So you just, first thing you do, you pick the template. You load your file, and I will show you how to load or not ROCKE-3D. But let's do this, pick one of these templates. We do load the file. We have it here, great. The next thing we do is we're gonna set geometry. Okay, let's say, imagine that you want to do transit for this planet. So you click here, it says primary transit, and then you are seeing the night side of the planet because the planet is looking at we're looking at the night side of the planet right now. And then you say, we're gonna keep the molecules default coming in the thing, which is all these molecules and all these aerosols. And these are we can change the instrument here. We can say, we can pick any planet. Yeah, look, I'm gonna create a thing, something like this, very standard, 200 microns, 200 resolving power. We're gonna do ppms, which is a nice unit. And you saw that I click a lot of things very fast, and you wonder, how do I know to do all those things? And I know it's like everything is a little bit of a learning curve, but I've been trying to document. If you click on this little eye here, it tells you things about the parameters embedded into things. So about the units, they are also explained here. So once you familiarize, even though they look like a lot, there are not a lot of actual inputs. There are only 3 windows with inputs. Once you learn them all, it will become very easy to run them. They are pretty much standard things. So I know that it will take some learning curve how to play with those things, but they are not complicated. That's what I'm trying to say. And the best thing you can do is always pick a template and start from there. So in this case, we say we are picking a simulation between 0.4 microns and 20 microns, with a resolution of 200 resolving power, and we want to see how the contrast looks in ppm for this planet. Okay. So we're gonna go back to this guy here, and then the machine asks for this number here, spatial binning. So remember, we have this planet has a lot of points across the limb. So if because we have so many points, it will take a long time because you have to compute transits at every location and then add them all up. So for the time being, I'm gonna do like this. What I'm saying here is, don't worry, I just add all these profiles and give me one profile just for speed, and do one transit on, instead of doing the thousands of, you have to, just for sake of showing, just being all the profiles and give me one profile and synthesize the transit. So in this case, so this is how the transit for this particular planet looks in parts per million, and these are the in the unit. So you can this is actually transit of the planet. You can actually see it right now, and you can do zooms and see the features and everything. So this is already, the simulation is done. But again, it did add all the profiles in the limit. It didn't do the 3D thing that you wanted to do. So I'm gonna drop it to 20 now. So I'm gonna bin every 20 spatial points, and so it will be 10 times slower, but at least you can see what it's doing. So now the machine says that it's going to compute 5 transits, and it will it will compute the 5 transits, and it will add them all together, and it give you this, which is this spectrum right now is the addition of all the 5 transits into one. And if I put here now 10, so now you have 10 sounds. And of course, if you put no binning, it will do. We can let's do no binning now, and you can see that it will do all the things. So it will take some time though. So now I have to do 90 simulations, as you can see. It will take some time. But what I'm trying to say with this is that once you have set up, so the main thing you need to understand is you set up the geometry, which is the orientation of the planet, load the file, the template, and then you run the simulations for those things. But before you do all that, I think it's recommended that you familiarize with those 3 elements in PSG, the geometry, the atmosphere, and the telescope, so you know what goes inside these things. And this case is running 90 transits across the disk to create this very accurate transit spectrum. It's doing one by one. My recommendation when you do these things is to always start to play around with things using a very high degree of binning, let's say 200, just to see that it will do one transit, just to see that things are popping up in the right way. I wouldn't run this very accurate calculation if when I'm about to submit a paper for publication. But before doing that, it's recommended you concentrate on doing a single simulation with a lot of binning. So I'm going to show you, after this, I'm going to show you a coronography mode, which is the other case that in case you're looking at the planet from, instead of looking at transit, you're going to be looking at the full disk. So now we'll compute the spectra across the planet. And then we're going to load a ROCKE-3D file into, an actual ROCKE-3D file into the simulation. It's almost done. Yes. So you see the spectrum didn't change much, of course, more accurate, but because we know that it's not going to be that different, but it's good that we know that this simulation includes all the individual points from every location across the disk. So imagine now that you want to do a coronography mode. You want to put the planet to the side. So you would tend to put, so just to remember about phases. So 180 is the planet is in front of the star. That's 180. 90 will be to the side. 0, the planet is just behind the star and then to the side. So it's moving across in its orbit. So if you put 90 and put this emission, you effectively tell the planet that you want to be looking at half. You're looking, this is the day side. You see, the sun is to the side, and then the other side is the night side. And then you say, okay, give me a transit spectrum. I'm going to put heavy binning so it's fast. And it give you a transit spectrum. This is how the planet looks like. It is simulation of how the planet looks like. And you can see the contrast in the optical is almost nothing, because a lot of the planet is in the night side, and you start seeing this more contrast happening in the long wavelengths. Of course, because the planet is warmer, is colder, sorry, than the star, and it produces the maximum contrast at longer wavelength. But you can see, you cannot see much. There's a lot of information here. So one of the things you can do is you can come here and do the log plot. I'm gonna do it again. And then you can see that actually in the log plot, you see the actual, this is the reflectance of spectrum of the planet, and this is the emission. You also see those two warnings, and you're wondering, what the hell are those warnings? So right now, we are doing a scattering calculation. So the machine is following, it's a multiple scattering, following the photons across everywhere on the planet. And water, which are liquid water droplets and water ice particles, they have a very complicated scattering pattern. And we are defining, we did a calculation. In this calculation, we are using a very simplified scattering mode, and it's called the number of stream pairs and Legendre polynomials. And this is a very technical thing, but it's about how the precision of the scattering function. And I put a very simplified one for this calculation, and the machine is telling you, if you want to do it super accurate, you should go to very high numbers of Nmax and Nmax to do it right. I wouldn't worry about it. It just is a warning to tell you, watch out. This is not at the 1% precision, but it should be enough within 5-10%. So I wouldn't worry much about it. But it just is a warning of PSG to tell you, you may want to do include more scattering parameters to make it accurate. And I wanted to show you now to do how we do the thing with the file. So I'm gonna open there. Okay, so for an example that we did the other day, and let me see if I here. So for an example that we did some time ago, we had So for example that we did that some time ago, we did is we picked 3 files: the AJK file, the IGL file, and the AGA file from ROCKE-3D. And the idea of these Python scripts is it takes those 3 files from ROCKE-3D, and it will create binary file for PSG to that it can be ingested inside PSG for a simulation. And effectively, what you do is you set the name of the files here, and then the machine will read different information compounds for different things. For somebody, from the AGAK file, it will read the information about the winds and information about the pressure structure of the atmosphere. For the AGAL file, it will read information about the location of the water ice clouds and the liquid water, and the pressure and the temperatures for every grid point. So it has a 3D information for layer by layer, no? And from the AGA file, it will take information from the surface, like that run albedo. So, in this particular file, we only took, instead of looking at the variability of the planet at different times, we only picking the one instance, the latest point on the file, and that will consider that to be the steady state of the atmosphere. And it takes that thing in this Python script, and it creates a PSG file. This is the file that just saves all the parameters, and it saves it as a binary file. That is the file that is being loaded into PSG. So once you run the script, it will create a file that looks, in this particular case, the file is called psg.gcm file, and it's the file that is the output of this particular output. Then you come here and you click here, it says load psg.gcm file. You put the name of the file and it will load it. I'm not gonna load it now because I did some change. But effectively, when you do that, you click on the file and the file name, and you put open, and it will open that file. And I have it here. So this is this particular case, and you can see this file looks like this. If you see something that looks like this, that you can see winds, temperature, things like that, it means that you load the file right. If you don't see anything, everything looks dark or whatever, it means something going wrong with the script. You need to go back to the script and find out that everything is working fine. But typically it should work. That we have tried the scripts with different things, and it should work. So it should give you a file that looks like this. And you can also look at different variables and make sure that the variables are being ingested in the right way. So once you have the file ingested here, go back to the thing. You say I want to do the planet at a phase 90, which is that thing, and then you do general spectra. And well, I didn't put the right file. Sorry, I didn't have any. I don't put. There are no molecules in this particular file. but it will run let me go back and pick another one that I was doing right. So I'm gonna pick this one. And it give you the simulation there. So I think the best thing right now, I'm almost running out of time. So I think best thing is to ask me questions, and then we can go into more detail into the little things inside the code.
Okay, great. Thanks a lot, Geronimo. That was fantastic. So any quick questions for Geronimo before we take a break for lunch?
Yeah, maybe one question. I see there is two Rocky model, ROCKE-3D TIE and ROCKE-3D Earth. What is the difference?
Yes. So those are examples, we can call it. They're all ROCKE-3D outputs. They are the same. This is the same GCM. It just I put here some examples for people to play with, to familiarize with the tool. So these are different simulation runs that I put as people to familiarize. So if you look at the ROCKE-3D Earth, this is a simulation of ROCKE-3D of an Earth planet. And it's a ROCKE-3D simulation, so it has the same fields as a ROCKE-3D simulation, but they are for ROCKE-3D, of course, and for Earth. And then if you do this one, this is for a simulation that is an intercomparison with different GCMs. It's called a TIE intercomparison. And this is for an aquaplanet, and this is ROCKE-3D running for that particular case. But again, these are all just examples for you to play with. What you have to do is you have to run this script yourself, create the GCM file, and then load it here, and it will give you your actual file that you want to run with.
Okay, the scripts are the same then?
Yes, the script is the same.
Yeah, Geronimo, could you point out where you download the script from?
Yes, good point. So when you click, for example, you click here, it says ROCKE-3D TIE, and here there are the scripts. And if you click in TIE, click in Python. So this is the script that you can download, and you can just download and run it yourself. And then if you go back, and then if you are old school, no IDL, do IDL, this is the IDL version of it. So the thing is this, these are the different examples just to say, but the scripts are all the same. This is for ExoCam and for ROCKE-3D, they are here. You can just download them there. And if you, again, so as you saw, in order to run the tool, you need to familiarize a little bit with the way PSG run the simulation. And I know there's a lot of information content there. There's a lot of, like every tool in life, you need to know what goes in and what goes out, no? So it can be a little bit overwhelming. I try to make it as digestible as possible, what I was showing you, but I know that when you actually want to run yourself, you're going to be encountering some things that you don't understand well what's going on. So what I do recommend is you go here, in the upper part is all the help, all the things here on the top are the help. So if you go to these tutorials here, this is a video that I produced one in 2019. It's a 1 hour long video, but it tells a little bit about how to run the tool. So I think at the end of the day, I don't know if you want to spend 1 hour watching that video, but if you want to run a simulation, it's better to go for that. Even though it's generic, it tells you how the code operates. And I think once you know more or less how the code operates, it becomes much more natural. Most of the doubts will become much more clear after watching the tutorial.
Yeah, John, there was a question from one of the participants asking if it's possible to run the downloaded version on multiple threads.
Yes. So good point. So as you are here, I'm going to show you, for example. So here, this is the online thing. This is the tool. You can run everything from here. But of course, every time you make a simulation or every time you upload a file, the file is going to a server, Goddard, that runs on Goddard, then it gets back the data. It's good for testing, and I definitely recommend you do that first. But then in the long thing, you want to script this, you want to put multiple machines running and do the full command. So in order to do that, there's something called the application program interface, or API, and it's here. If you click in remote operation, it's here, the API system. So effectively what you do is you will send what we call a configuration file that summarizes all the inputs to PSG, and then PSG will give you back spectra. That's the way it works. You can do the scripting back, process. Again, this API will be sending things to a NASA server at Goddard. So again, you can script it, you can run, thousands of phases, every 1 degree as you want, but it still will be running with the Goddard server. So you at least you can script it, but it's still slow. So the next step will be to say, okay, this is great, but I want to have my own version in my own machine, and I want to run it as many times as I want and do whatever I want. So for that, there's something called the Docker. And what is Docker? So Docker is a virtualization system. What it does is you first install Docker. It's a software in your machine, and that creates a virtual machine where a local version of PSG can be installed in your machine. And of course, PSG is a huge package, has a lot of stuff. These are terabytes of data. You can just install terabytes of data in your machine. So what you have is packages. So if you have the Docker version on your machine, you start adding, basic packages for the thing, and you create your own little PSG tool, and you can put it in multiple clusters. For example, at Goddard, I have a little cluster with 20 PSG clones, which are all Docker based. And I gave them, different things to run them in parallel, and I can run a big machinery for that. The explanation of how to run Docker and all those things is actually, you may think it's complicated, but it's not that complicated. It's actually pretty simple. And I have tried to document it all here. So if you want to go with the Docker version, which I definitely recommend if you're going to do heavy runs, this is how you install the Docker version of PSG in your machine. It's definitely not complicated.
Okay, great. Any other quick questions for Geronimo?
And again, also please send me emails. Even though you think that you are stuck in something simple, I'm certainly able to help, and solving small things and glitches with the software. And also I learn more about it. So the more we can serve the ROCKE-3D, the more easier for other ROCKE-3D users it becomes. No?
Absolutely. Okay. Well, thanks again, Geronimo. That was fantastic. I think people are really excited about using this.
Perfect.
So we take a break for an hour, or I guess maybe 10 after the hour. We start up again to give people a full hour of lunch break, and then we'll continue in the afternoon. If you have more questions,
let me just say something real quick.
Yep, go ahead, Chris. Mention your thing before we take off.
Sorry. Okay. Yeah. Let me just share my own screen real quick. So on slide for my thing later is sort of a kind of a summary of everything we've talked about the last 2 days, and going through an example of a Proxima B run deck. If you actually do want to join along and sort of run the simulation as well, the second link here on slide 79, you can download a few of the input files. It should take you about 10 minutes. Just the run deck, the .r file is, you just put that in your the dex directory, and then the rest of the files in that folder, they're all input files, topography, and all those kind of files. You could just put those in your prod input files, and then I think the only thing you'll have to do is in the run deck file, you'll just have to add this line. This is in the guidance as well for the installing ROCKE-3D. Just put in the so it knows where the SOCRATES files are. I think that's all you should do, but if you do want to follow along, then try to find time to do that in the next hour. Because hopefully we'll just be getting to the point where we're generating sort of an ACC file and then showing that example.
Great.
That's it.
Thanks a lot, Chris, and thank you again, Geronimo. So so we'll take a break, and we'll join back in about an hour from now.